Okay, so what happens now if we end up with a situation, same mass, same spring, okay, same impact when you displace it, you let go, the spring is going to force it back, but this time I'm also applying a force to the mass. Okay, so not this mass spring system actually has a force being applied to it, and that force is probably some function of time, which is like a bracket t. That could be a constant force, in which case it doesn't matter what time you've got it; it could just be a constant force. But this time I'm actually applying a force that's going to vary with time, and that force is going to be a sinusoid. But we'll look at that in a second. Okay. Again, Newton's second law. You can stick it in. Sum of all the forces is mass times acceleration. So I've got my spring force being applied. Okay, and that force as a function of time. So again, if I draw my three-body diagram, okay, I'm saying x is this way. I've got a force being applied this direction, which is my function of time, and I've got my spring force Fs in the opposite direction. Okay, so again, I've got minus kx plus the force that's being applied. I put all the x terms on one side, then x over dot plus kx equals Ft. And like I said, this time I'm actually going to make the force a sinusoid. Okay, so I'm applying a sinusoidal force to this system. Okay, I'm actually applying force to the mass to move it backwards and forwards. Notice that in this case I've got F0, which is the amplitude that I've chosen for the force that I'm applying. So that could be 80 newtons, it could be 800 kilonewtons, whatever. That's the force that I've decided. And I'm also vibrating at a frequency that I've chosen. Omega, without the subscript, okay, has nothing to do with the system. Okay, it's to do with what I've decided. I want to shake it at 20 hertz. It might want to shake on its own naturally at 5 hertz or 200 hertz or whatever. I've decided that I'm going to excite it at that frequency because that's my decision. Okay. So, for example, imagine you had an engine on an engine mount, okay, in a car, and there's obviously engine mounts do have some element of elasticity in them, okay, in the sense that there's a spring, and obviously engines oscillate, depending on what sort of engine you've got. There's a frequency of oscillation, and obviously that frequency of oscillation is of your choosing. It depends on how fast you're driving the engine. Okay, it doesn't matter what the engine mount wants to do. Okay, this is the frequency that you're creating as your decision. And like I said, the force is also your decision. And so the system has to respond to that oscillation. Okay, and the way it responds is that as time goes off to infinity, you ignore the initial conditions. The engine, the actual mass, will end up oscillating at the frequency that you chose. Okay, it doesn't care what it wants to do. Okay, eventually what it wants to do will die away because it's damped or whatever, and then you end up with a system that oscillates on it at the frequency that you've chosen. So what we're working out is what's known as the steady state solution. And if you go through the processes, okay, we apply a trial function. Okay, in this case, we know that it's going to. We make an assumption that it's going to oscillate. Okay, so we try a trial function. We don't know what A is, but we know what omega is. Okay, and if you go through the motions, take the first and second derivative of this trial function, stick it in the first, second, and then the second derivative. You can see that we've just got a minus omega squared come out the front. And this A cosine is our trial function, so we can replace that with x. You stick that in the equation of motion, okay? And you end up finding out that, there you go, I've stuck it in. So I've taken this bit, I've stuck it into where we had x over dot. I've taken this and put it where we had x. mx over dot plus kx equals f naught cosine omega t. The cosine omega t's can disappear, okay? Because you've got one on this side and one on this side. You end up with A being f naught divided by k minus m omega squared. So there's the next motion. So your amplitude in that equation is now not defined by initial conditions. In the previous free oscillation, okay, it depended on where you started. Did you pull the mass back and let go, or did you give it a kick? Initial velocity, okay? Now it doesn't matter what you did at the beginning, okay, because the steady state solution, as time goes into infinity, will have this amplitude and the frequency that you decided to give it. Okay. So based upon the force that's been given and the characteristic system and the frequency in which you've driven it, you can determine the amplitude and the frequency. So that's the complete solution for a driven system. And that's one of the distinctions between driven and free systems. Free systems will have some arbitrary constants, okay, that are adjustable. Okay, it depends on where you started the thing. Those things can be determined based upon what's known as initial conditions. For force systems, okay, if we're looking at force systems, in this chapter we're going to focus on what's known as the steady state solution. So it doesn't matter what happens when time is 0, because the amplitude and the frequency, and in the case of a force damped system next week, we'll also look at a phase involved in that. Okay, they're going to be determined by equations that are based upon the force that's being applied and the system itself. Okay, so like I said, there are no adjustable constants. So for free systems, both damped and undamped, there's going to be adjustable constants in there. For force systems, free and for force, damped and undamped, then those things are not so adjustable. They're based upon what you've decided to give the system. Okay. So like I said, A is no longer adjustable. A is this amplitude. Okay. And we can also look at what happens to this as omega changes. What happens to an A when omega changes? Okay, we can what does happen to it? Let's play with some of the numbers, okay? So when this number becomes very small, this approaches 0, okay? A is going to be F0 divided by K. Yeah? F0 divided by K, which is a constant. And if you think about that, okay, if you multiply A as a displacement in meters, you multiply that by the stiffness, you get a force, won't you? Okay? And that's called static displacement. Imagine the system isn't oscillating, it's just sitting there, okay? F equals Kx, or in this case, Ka, or A equals F0 upon K. And F0 upon K has a name, it's called static displacement. Okay? What about if omega goes off to infinity? Okay? We get really, really fast oscillation. Okay? Well, essentially, we're going to have F0 divided by something that's very, very huge. Okay? Very, very huge. And what's something divided by something very, very huge? What's that going to equal? Something divided by infinity? Well, it's going to be pretty much 0, isn't it? Okay? So if you vibrate something really, really fast, okay, the actual amplitude of the oscillation is probably going to be very small. Okay, you'll get to a point where you won't be able to notice that that's actually moving if the amplitude is really fast. Okay. What happens if omega is very close to the natural frequency of the system? Okay. What happens if omega is very close to the natural? Well, what happens here is that if you go through the motions, if you stick in k upon m in here, or root k upon m, and obviously square it becomes k upon m. Well, you end up with k divided by m in here because it's squared. Okay. The m's cancel, we end up with k minus k. What happens when the bottom is 0? What happens to the amplitude?
Well, it's going to be equal, right?
Yep, it goes up. It's infinite, basically. Okay. So you end up with situations, and that bit in the middle, where they equal each other, okay, that's known as resonance. Okay, and resonance can be bad used. Can be used advantageously, but like I said, you don't really want, when you're driving a system with a sinusoid, you don't really want to drive it at this natural frequency, because you end up with amplitudes that can end up destroying the system. Okay. So like I said, so when omega's naught, okay, you stick in omega naught, you get F0 upon K, static displacement. When omega's massive, you end up with A equals 0, because on the bottom you've got a massive number, okay? And when omega is equal to the natural frequency, you end up with either plus or minus infinity as it happens. It's undefined, but it's massive. And like I said, that's the problem with going. We'll talk about resonance in a bit more as well. But like I said, that's a good thing. So you can plot this, okay? And if you plot, this is m is known as the amplitude ratio. So that's your amplitude divided by that static displacement. And clearly, when A equals F0 upon K, you end up with that amplitude ratio of 1. And obviously, as you approach, and this is the frequency ratio. So you take the driving frequency and you divide it by the natural frequency. So obviously, when this is 1, okay, you're actually driving out the natural frequency. Obviously, when this is 0, you end up with down here. And when this is massive, compared to this, you're up this side. Okay. And this is amplitude ratio. And you can see that as you go from zero frequency to the natural frequency at 1, it's going off to positive infinity. It comes back from negative infinity, okay, and then goes this way. So this half of the equation, you might be applying a force this way, but the thing's actually moving that way. You get this at 180 degrees out of phase. Okay, and this obviously this way, you apply a force. So you go past the point of resonance, and like I said, you end up with this 180 degree out of phase. Although the force is going this way, the thing is lagging behind you by 180 degrees, actually moving in the opposite direction. We'll talk a bit more about that when we talk about damped systems. So, another question. A mass spring system with a vehicle, within a vehicle interior, okay, with an effective mass of 2 kilograms and a spring system of 45 newtons per meter, okay, is subjected to an oscillating force function described by Ft. F of t is 10 cosine of 3t. Okay. What is the steady state amplitude of the resulting oscillation? So I'm looking for that value of A. Okay. Now, do you want to have a go at this without me helping you, and then we'll go through the solution, or yeah, with that? I think we've got time. I've got a few of these in-class questions, but I don't want to run out of time. So I'll give you 5 minutes, and then we'll go through the solution.
And by omega squared. Well, what's omega?
Okay, so if we go through to solve this, we've got A is F0 divided by K minus M omega squared. Okay, and that's the driving frequency, not the natural frequency. And so in this case, we've got F0 equals 10. Omega is 3 radians per second. K is 45 newtons per meter, and newtons, and M is 2 kilograms. Okay, so we've got 10 divided by 45 minus M, which is 2, omega squared, which is going to be 3 squared. 10 divided by that comes out to be 0.3704 meters. Okay. There's the amplitude of the oscillation. So if you were to write this fully as a solution, x of t, then with x of t, okay, you'd end up with that because, like I said, the oscillation will be the frequency at which you're driving it. Okay, and the amplitude is based upon the system conditions.
Do you generally have your answers in 4 significant figures?
Generally, yes.
Okay.
Partly because I work out my answers using MATLAB, and MATLAB defaults to 4 significant.
Okay. Well, no, it's just all lecturers are a bit different.
Yeah.
Like Peter Kay, he doesn't use MATLAB, so his answers are a bit different.
Yeah.
I use MATLAB, so it's all a bit confusing.
No, basically, I mean, sort of 4 figures is fine. Generally, what you're doing, if you're doing a problem using your calculator or MATLAB thing, you know, save your answers to the full significance in a sense. You know, use the memory function of a calculator. I think if you've got a scientific calculator that's automatically got 7 memories or 8 memories or whatever. Use them and obviously take your values forward. Okay, so say you worked out what omega is to be some decimal number. Yeah, use that to calculate it as opposed to some approximately you might have written before. Okay.